So our next speaker, the last one for this session, is Andrea Bracco. And he'll continue some of the stuff that we've been seeing with Planck. And the title of his talk is The Magnetic Field Structure in the Solar Neighborhood with Planck, a case around the South Galactic Pole.
Hello? Can you hear me? No? I think I can shout, and usually I speak up. Yeah. I will try to be short, as short as possible. Although I wish I could speak as Josh or Joanna were amazing in resuming, let's say. So Marco Ton already introduced me before, thanks. But today I want to speak about the work on the relative orientation between structures of matter and magnetic field as traced by Planck. I will focus on another work that characterized the last part of my PhD thesis. And I thank the organizers actually for letting me speak in here today, as Nezana was actually in the part of the committee of my PhD thesis. Most of my main collaborators are listed here below. And this work on characterizing the magnetic field structure in the solar neighborhood actually had two main motivations which drove this work. The first one, which is maybe more interesting for this kind of conference, is really trying to characterize magnetic fields in the ISM. The other one was driven by the effort of the Planck Collaboration in characterizing dust as a foreground for cosmological purposes. So this is a kind of obliged slide for me, as I'm on behalf of the Planck Collaboration, but I invite you to go and to download the data that are actually available at the sub-millimeter wavelength that are very useful to characterize the galactic physics. Well, actually, the galactic magnetic field as probed by Planck. So I invite you also to come, and I can give you these links later on. So I will go through a very brief introduction. We already saw yesterday some pictures like these. The main idea is that I believe that magnetic fields are very important in regulating galactic evolution and dynamics. In external galaxies, ordered very well, magnetic fields are seen different ranges of scales, both in age-on galaxies and phase-on galaxies, here traced by synchrotron polarization. And magnetic fields show both ordered components and turbulent components. What we want to do in the Planck data is trying to see if we can actually see in the Milky Way this footprint of large-scale magnetic fields. So despite the fact that in the Planck Collaboration, Tess Jaff, for example, led this work where she was really trying to model the dust polarization from Planck using complete models, analytical models for galactic magnetic field. And we had very hard times actually in doing so using models which are basically based on synchrotron data and Fourier rotation. In this work, we aim to do something simpler. Okay, so we don't want to model the galactic scale magnetic field. We want to see the footprint of this large scale in the more close by regions in the solar neighborhood. So, and we do this through dust polarization. I don't have the time to go through the details of how can we actually use dust polarization to trace magnetic fields, but here I want to stress some basic points which are at the base of our analysis, which is this one, first of all. So across this talk in this work, we assume that the intrinsic dust polarization is homogeneous across the sky. So all the variations in polarization, in dust polarization that we are seeing, we don't relate these variations to dust properties. Of course, this is a big assumption, but I will try to convince you that in the medium that we are analyzing, it may be very likely this to be. And then I want to stress these two main observables that you can directly reconstruct from the Stokes Q and U parameters, which you directly observe with the Planck satellite, which are the polarization fraction and polarization angle, which both depend on the galactic magnetic field morphology. For the polarization angle, it's trivial. This is the perpendicular orientation of the plane of the sky magnetic field. For the polarization angle, is less trivial, but basically the polarization fraction that we see depends on the mean orientation of the magnetic field with respect to the line of sight. And as Marc-Antoine was saying, it clearly depends on the tangling of the magnetic field along the line of sight. So we'll try to characterize the local magnetic field structure using these two observables. Of course, this study was highly motivated by a previous work by Carl Heiles, who almost 20 years ago, he studied the local direction of the galactic magnetic field from starlight polarization. Here, what we're trying to do is using dust polarization now in emission instead of in extinction. And here I'm showing the Planck data from another perspective. I'm turning around the sky and focusing around the South Pole, which is at the center of these circles. And here, this is the dust model for total intensity that Marc-Antoine described before, and the Stokes Q and U parameters. First of all, I want you to focus on the Stokes Q and U parameters and these striking patterns, these butterfly patterns that we see around the pole. And I will come back on these in a few slides, and that we relate to the ordered magnetic field in the solar neighborhood. The same kind of information we can actually look into the polarization angle. Actually, here I'm showing the B field orientation, so 90 degrees from the polarization angle, and the polarization fraction, as I was telling you before. These parameters are showing that in the South Pole, at high latitude, where we have the least dust column density along the line of sight, and so we're focusing on more local stuff, we have very organized patterns in the polarization angle or B field orientation, although there is some dispersion around this very ordered field. As well, we can see that also at very high latitude, we can see that the polarization fraction has values which covers a wide range up to almost 30% in polarization fraction. So what we want to do actually is trying to explain these dispersions in polarization parameters through the magnetic field structure, in particular introducing first step the ordered field component, and then the turbulent field. We're using a toy model, okay? So it's a very simple approach which has a lot of approximation, but in this case, simpler is better for me. So first of all, for the ordered field, the first step, we are using a very simple approach where we only take into account geometric effect. This is really inspired by the work that Carl did in '96. So basically, if we assume that in the solar neighborhood there is a fixed direction of the magnetic field, the only the fact that we are looking we're looking at this fixed direction from different lines of sight will produce some patterns in the Stokes Q and U parameters that I'm showing you here for a given direction of the field towards these galactic coordinates. And here you can clearly see these butterfly patterns that I was showing you in the data. So the aim of the game here is trying to find the best the fixed direction of the field, of this order component of the field, which fits the butterfly patterns of before. So this is what we do. It's very simple. We do a kind of a linear regression using different fixed direction of the magnetic field. And we fit also for the average polarization fraction below minus 60 degrees. And this is the mean direction of the field that we find around the South Pole. So for galactic longitude towards 70 degrees and latitude towards 24 degrees, and an average polarization fraction of 12%. This, we know that it's a lower limit to the polarization fraction, since so far we didn't consider any line of sight effect. So the next step is actually trying to quantify the dispersion around this mean orientation. So without going to the details, I just want you to show that what we do is basically we rotate the reference system of the Stokes Q and U parameters, so that for each point in the sky, now the Q and U are really showing the dispersion around the mean field orientation that we have just found. And this is the histogram of the dispersion around this mean field orientation that we relate to the turbulent component of the galactic magnetic field at high latitude. In particular, we assume a very standard approach where the magnetic field in general can be written as the combination of an ordered and turbulent field, and where the dispersion of the turbulent field with respect to the ordered field is directly related to the dynamic properties of the medium that we are actually probing. So to introduce the turbulent component, we use two steps. The first one is we produce Gaussian realizations with on the sphere with power law power spectra for each component of the turbulent field that we add to the mean field that we found before, which will depend on the ratio between the dispersion of the turbulent component with respect to the order component. And the second step to introduce the effect of tangling of the field along the line of sight is a very simple approach. We basically produce the same kind of realization, but we add different polarization layers, several polarization layers along the line of sight, which will share the same ordered field, but a different turbulent component. So basically, we are able in this way to build several layers of polarization with the same order component and reproduce the polarization fraction and polarization angle. So to produce some modeled distributions of polarization fraction and angle and fit with the data. The main parameters in this game are the intrinsic polarization fraction, this ratio between the turbulent and ordered component of the field, and the number of polarization layers along the line of sight. Okay, and then we produce several realizations to take into account the variance of the random component. So I'm going directly to the results. Here you're seeing in black the data, and I'm showing the distribution of the square of the polarization fraction, and in colors the model for the polarization fraction and for the polarization angle. So as you can see, we can roughly reproduce the distribution of these polarization parameters in the Planck data, assuming, finding a best fit triad of parameters in our model with a intrinsic polarization fraction at high latitudes, which is very high, it's 26%, a ratio of the turbulent to order component of about 1, which suggests equipartition in this medium, and several but few components of polarization along the left side. I'm concluding then, stressing again that the interpretation of the polarization data of Planck has suggested so far that the magnetic field structure is playing a crucial role in this in the polarization, in the dust polarization data. And then we can reproduce the one-point statistics, the histograms of polarization angle and fraction, assuming a very simple model for the ordered and the turbulent component of the field. What is a bit open still is the interpretation of these layers that we use along the line of sight. There might be different density structures along the line of sight. There might be the hint of some correlation length of the turbulent component in this diffuse medium. And this is why we're also doing, there is a follow-up paper which is investigating actually the power spectra of polarization and intensity. With this, I conclude, and I invite you to I will take questions, but also to look in more details at this paper, which is now on the archive. And you can also check this webpage, which resumes the results of Planck, that the Planck Collaboration did in galactic science in particular. So thanks a lot for your attention.
It's good that you are able to reproduce the Planck polarization. However, I feel that your model has a lot of free parameters, and these layers are not layers. In fact, these are the correlation length of the turbulence, and you cannot just take 20 layers or whatever you. Taking arbitrarily. This is my first concern. And then there is this issue of traditional presenting turbulence as mean and isotropic random field is also not true.
Yeah.
So we have a lot of information, and Blakesley was working a lot about on developing different techniques, how to obtain the statistics from observations, and then I think it could be a very useful input to your
I totally agree, and I'm interested to actually discuss further. Thanks.
One last question.
I wonder if you give us an idea about the distance away you're actually probing the magnetic field. And a related question is, we saw, I think, some data earlier showing how the polarization, how this correlation that you employ is not a strong one. That is to say, the dust polarization varies a lot from one region to another. And is that a problem for you?
Could you, repeat the question, the second part of the question, please?
If the volume that you're probing is small enough, perhaps it's safe to ignore the spatial variations in the dust polarization properties in response to the magnetic field. And I'm just wanting you to comment on whether that's an issue for you or not.
So we are actually looking at very high latitudes. So regarding the scale heights of the region that we're looking, we believe.
But what is typically the actual physical distance that you think you probe?
A few hundred parsecs is.
Right.
Yeah, something like that. And dust variations due to dust properties, we actually don't think we are in the medium where these effects can be very important. Also because there are not real, radiation sources around apart from the galactic radiation field. So
let's thank Andrea and all the speakers in this session.